Look at this rapidly shifting face. It is a completely synthetic identity, morphed in real time by an algorithm. Autonomous chatbots and generative models are suddenly everywhere, creating an overwhelming flood of artificial content. But this ubiquity has brought a lot of confusion. People often use terms like AI, machine learning, and deep learning interchangeably, as if they all describe the same thing. To sort this out, we need a baseline definition. At its core, artificial intelligence is the technological quest to match or exceed human cognitive capabilities, specifically the ability to discover new information, infer meaning from context, and reason through problems. This diagram illustrates how these technologies actually fit together. AI is not a single tool. It operates as a series of nested layers, with each inner circle representing a specialized approach to achieving that broader human-like cognition. To understand how machines in the center of this diagram recently acquired the ability to create entirely original content, we have to look back at the historical computing bottlenecks that forced developers to build these layers in the first place. In the 1980s, early AI research relied on programming languages like Lisp and Prolog to build what were called expert systems. The architecture of these early systems was strictly manual. Every single action the computer took had to be governed by a rigid, human-coded rule. This created an immediate bottleneck. If a developer did not explicitly write code for a highly specific scenario, the machine would simply halt. It could not adapt to anything outside its literal instructions. Developers hit a ceiling. No human could ever write enough lines of code to account for every nuance and edge case of the real world. For a system to handle true complexity, it needed an architecture capable of observing data and learning from it without a human programmer. By the 2010s, this realization led to the first major evolutionary subset of AI, machine learning. Machine learning stripped away the manual rule writing. Instead, engineers fed massive datasets into algorithms, allowing the computer itself to sift through the numbers and discover underlying statistical patterns. You can see this pattern recognition in this data sequence. By establishing what normal behavior looks like, the machine immediately flags any deviation that breaks the pattern, a technique used in cybersecurity to catch network intruders. Engineers refined this further into two methods. Supervised learning guides the system using human-labeled data, while unsupervised learning allows the machine to find unstated patterns entirely on its own. Probability-based prediction replaced rigid instructions, allowing computers to solve problems that were far too complex to manually code. Human thought is multivariable and nonlinear. To tackle logic that doesn't follow a straight path, engineers built an even deeper subset of machine learning, known as deep learning. This web of glowing nodes illustrates how deep learning works. It relies on neural networks that pass information through multiple interconnected layers to evaluate a problem from countless angles simultaneously. Look at what happens to the middle layers here. They become so densely interconnected that it creates a black box effect. The system calculates a correct output, but it is often impossible for engineers to trace exactly how the algorithm derived that specific conclusion. By trading away the ability to see every internal calculation, researchers gained the power to solve multivariable problems, like real-time image recognition, that had stalled for decades under previous methods. That structural leap directly enabled the most recent architectural layer, foundation models and generative AI. Large language models, or LLMs, take the predictive statistical analysis of a neural network and scale it. Instead of merely guessing the next word in a sequence, these models map language well enough to predict entire sentences, paragraphs, and long-form documents. A common criticism is that generative AI is merely regurgitating existing data. However, consider the analogy of musical composition. Every musical note has already been invented. A human composer creates an original song by recombining those existing notes into a novel sequence. Generative AI operates on a similar principle, recombining massive datasets to draft original text, generate distinct audio tracks, and render brand new video. These foundation models represent a pivot. Machines that once only analyzed human reality are now actively generating it. This chart plots AI adoption over time. For decades, the technology remained highly theoretical, tracking as a flat horizontal line. But the introduction of foundation models triggered this near-vertical spike in global integration. In this microscopic view, we see this surge applied to medical research. Generative models rapidly summarize fast patient data and accelerate biological analysis, or synthesize audio to restore the voice of a patient who has lost the ability to speak. Yet, those exact same capabilities carry severe ethical risks. The tools used to restore a voice can be weaponized to create malicious deepfakes or automate the spread of misinformation at an industrial scale. Modern computing models now synthesize new information rather than just following a manual. We are no longer limited to the rules a human can type out. We are working with systems that can produce their own original work. Distinguishing between terms like artificial intelligence, machine learning, and generative AI is a matter of critical literacy. This is the essential vocabulary required to understand, navigate, and ultimately shape the future of human civilization.